worked through some steps or had an idea with how to get started with this. So the idea is to just plug in the solution and see that it works. So in order to do that, you can just compute the first derivative in time using the chain rule, and that requires differentiating this f by its argument, and then its argument is x minus ut. And so the first term in this expression is just going to have a t derivative of 0 because it's just the x term. The second term you break out by the product rule, so you get u sub t, and then minus u as your solution. And so now you have this equation that you can solve for ut, and you get u sub t equals minus f prime u divided by 1 plus f prime multiplied by t. Okay, so so that's your ut term. So this needs to be canceled by the ux term, and ux is computed in a similar way. You can differentiate using the chain rule again. So again, you have x minus ut as your argument of this expression, and you get f prime 1 minus u sub x t. Again, you have an expression that you can solve for just by rearranging, and you get that ux is equal to f prime divided by 1 plus f prime times t. Okay, so the questions about that? It's just plugging this implicit solution in and just using rules of differentiation. So if we want to check that this works as a solution, we plug it back into the PDE itself, and we have this term minus f prime u plus f prime times t plus u f prime divided by 1 plus f prime t. So we multiply through by that factor of u, and everything cancels out, and it's well and fine, right? Now, do you see any potential issues with what we just worked through that might come up? You can chime in if you want.
F prime t should not be equal to -1.
Exactly, right? So as far as some restrictions that we might have, well, the biggest one is that we do not want this denominator term, 1 plus f prime times t, to be equal to 0, okay? And the question is, okay, what sort of would this violate, okay? We want something more than just kind of dealing with this on a case-by-case basis, okay? So the biggest thing to note is that what did we start with? Well, we started with an implicit solution, right? So we had that u of xt was equal to f of x minus ut, okay? This is an implicit solution, okay? And in particular, its definition is governed by the implicit function theorem, okay? So the way that we can write this implicit function is we can say there's some function of x, t, and u that we want to always be 0. So u minus f of x minus ut, okay? should be equal to 0 in order to satisfy this. It's just another way of writing this implicit solution. So given then that your initial conditions satisfy this, okay? Certainly our initial condition should satisfy this in the first place, okay? Then we need, we can ensure that f of xt u will be equal to 0, okay, in some neighborhood, okay, of the initial condition, u x0 t0 equals u0, okay, given some conditions, okay? So I've run out of space here, so I'm gonna have to rewrite this on the next page. But the idea is that we need some condition that says, I have an implicit solution. I can invert that implicit solution to get some explicit function, okay? Or another way of saying that is, this implicit solution legally defines a function that I can actually use. You can write down plenty of implicit functions that actually can't be solved, right? Just like you can write down polynomials that don't have any zeros, for instance, okay? So I need to make sure that the implicit function that I've written down can actually be inverted. So I sort of half wrote down what I wanted to write, but so the idea is that given, okay, I'll rewrite all this. Given that x0, t0, u0 equals 0, okay, then f of xt u equals 0, okay, in a neighborhood of the solution u of x0 t0 equals u0, okay. In other words, it can solve, or we can solve for u of xt, okay, if, okay, and this is the condition that we need, the derivative of that function big F evaluated at x0, t0, u0, okay, is not equal to 0, okay? So this is just a statement of what's called the implicit function theorem, okay? I can't have the derivative of my function sort of defining this implicit function of u have a 0 derivative in that unknown function u, have a 0 derivative if I'm to be able to invert it, right? So this is, you can sort of think of this like, you know, this issue that you get with one-to-one correspondences when you plot things in the XY domain, okay? And you end up having like a 0 derivative there, right? What that means is that you could potentially have a function that has multiple values when you invert it, okay? So this is the kind of thing that you're ensuring by this position, by this condition. And in fact, this would imply that we need that, in our case, f of u, sorry, this should be f of x, t, and u, which we know to be equal to u minus f of x minus ut in our case, right? If we differentiate this with respect to u, then what we get is 1 minus f prime multiplied by t. Okay, sorry, multiplied by, just a minus sign there, negative t. Okay, And what is that? Well, that's just that quantity that kept popping up before. Okay, 1 plus f prime t. Okay, so if I evaluate this at x0, t0, u0, then this is equal to 1 plus f prime times t0. This needs to not be equal to 0, according to this condition on the implicit function theorem. Okay?
Professor.
So
So
yes, go ahead.
the derivative of f cannot be 0 in the vicinity of x0, t0, u0, right? But somewhere else it can be 0.
Yeah, so what the implicit function theorem does for you as far as this solution to the initial value problem is that it says you can be sure that you'll have a solution in some neighborhood of your initial condition, okay? But beyond that, it doesn't tell you you will have a solution for as far forward as you would like to go in T, okay? You cannot get a condition like that from the implicit function theorem. You need something else to give you that. But yes, what this is telling us here is that for sure, if this condition is violated at the initial condition, you're done. You can't get a solution to your initial value problem. Okay. So,
Zach,
yeah, go ahead.
it seems like this is really just saying that we can compute ux and ut, but it doesn't seem like it's unique to this particular PDE.
So, yeah, so there's two things here, right? So one thing is that we showed that, yeah, ux and ut would not be defined if this condition was violated, okay? And we said, is that connected to something that's deeper? And the deeper thing that we're identifying is that if you don't have this condition satisfied, okay, then you're not going to be able to construct a solution even near your initial condition. So the implicit function theorem is actually talking about whether or not I can construct solutions. The thing that we found by just plugging in the solution that we got was, yeah, something that had to do with computing ux and ut. But because that is the solution, it's telling us that solution is meaningless if this implicit function theorem condition is not satisfied. Does that make sense? Okay.
Yeah, I think so.
Okay. So this is sort of a vague example-based motivation of the kind of deeper issue that we'll see when we start to work through the method of characteristics, which tells us, you know, anytime you get a method of characteristics solution, which we'll talk about today, you're going to need to invert some functions, and you cannot invert those functions if you don't have this particular condition satisfied. So it says we cannot apply method of characteristics if a condition like this is not satisfied. Okay. So that sort of gears us up for the kinds of things that we're going to see now. Inviscid-Burger's equation can be solved by something called the method of characteristics, which we're going to go through now. But the idea is that oftentimes